Hello everybody, welcome once again. We are in our 6th module and this is our fourth video in the 6th module. So in the third part we saw about 3-hinged parabolic arches supported at the same level and one problem. Now this is the continuation of 3-hinged parabolic arches supported at the same level. So today we will see two problems. Two simple problems. So the problem is a 3-hinged parabolic arch has a span of 60 meter and a central rise of 10 meter. It carries a UDL of 10 kilonewton per meter over the entire span. Show that the bending moment is 0 at any cross section of the arch. So first of all we will draw the diagram. So this is a 3-hinged parabolic arch. We have 3 hinges, one hinge at A, another hinge at B and the third hinge at C. And this arch is subjected to an UDL of 10 kilonewton per meter over the entire arch, over the entire span of the arch. Now, the span of the arch is 60 meter and the central rise is 10 meter. So, our aim is to find the reactions at A and B, that is VA, VB, HA and HB. Then we have to prove that the bending moment is 0 everywhere. So at any section X, wherever you take X across the arch, your bending moment should be equal to 0. That is what we want to prove. So first of all, as usual, as we did in the previous problems, we take the moment about B is equal to 0. So we get VA is equal to 300 kilonewton. Also, we can take moment about A equal to 0 or VA plus VB is equal to total load, that is 10 into 60. 10 into the distance 60, we get 600 kilonewton. So we get VB is equal to 300 kilonewton. That is VA is equal to VB is equal to 300 kilonewton. Since it is subjected to an UDL throughout the span, the vertical reactions at VA and VB will be equal. So VA equal to VB is equal to 300 kilonewton. Now we are taking moment at C is equal to 0, we get H is equal to 450 kilonewton. So we have already seen the horizontal reactions at A and B will be equal when the supports are at the same level. Now you can take any support, you can take X either from A or from B. So here, so both you will get the same answer. Here we are taking the X from a distance of, we are taking the section at a distance X from A. So when you are taking X from A, the corresponding vertical distance is Y, and we know for a parabolic arch, Y is equal to 4hx by L square into L minus x, where h is the central rise, here it is 10 meter. Now, taking bending moment at any section X. So we are taking X from A, so our bending moment at any section X is equal to VA multiplied by the horizontal distance. So VA into X, it is left clockwise. So left clockwise for a bending moment, see when you take bending moment for a section, the left clockwise is positive and right anti-clockwise is positive. So here it is left clockwise, so VA into X positive minus H into Y left anti-clockwise, that is negative. So minus H into Y, again left anti-clockwise, so it is negative, minus this 10 into X into, that is the distance of the load, X into half of the distance, X by 2. We get VA is, we are substituting the values, VA is 300, X we don't know, so we will take it as X, H is 450 and y, we are substituting the value of y. We are substituting this y in this equation. So, we are substituting y minus 10x square by 2. So, we will get 300x minus 450 into 4 into, substitute the values of h and l. So, we get an equation like this. You can simplify this more. Now, after simplification, our aim is to show bending moment is 0 at any cross section. So, while you simplify this equation, you get it is equal to 0. So, anywhere you take, anywhere along the arch, that is when a three-hinged arch supported at the same level is subjected to UDL throughout the span, the bending moment is 0 everywhere. That is the meaning of it. So, for a three-hinged parabolic arch subjected to uniformly distributed load, it is not subjected to bending moment at any cross section. That is, bending moment is 0 everywhere. It supports the load in pure compression. You will have only pure compression. There will not be any bending moment. We will go for the next problem. A three-hinged parabolic arch has a span of 40 meter and a central rise of 10 meter. It carries a UDL of 10 kilonewton per meter over the right half of the span and a concentrated load of 40 kilonewton at a distance of 10 meter from the left support. Calculate the location and magnitude of maximum bending moment in the arch. So, we will draw the arch. So, it is given three-hinged parabolic arch. So, we have hinges at A, B and C. Our span is 40 meter. We have a central rise of 10 meter. We have a 10 kilonewton per meter loading UDL at the right half of the span and another 40 kilonewton concentrated load at a distance of 10 meter from the left support. Now, as usual, we get, by applying sigma MB is equal to 0, we get vertical reaction at A, VA is equal to 80 kilonewton. So, VA plus VB is equal to 240 kilonewton, that is this 10 into 20 plus 40. So, we get 240 kilonewton. So, VB is 160 kilonewton. Now, by taking sigma MC is equal to 0, we get horizontal reaction, H is equal to 150 kilonewton. So, at A 150 kilonewton acting towards the right and at B 150 kilonewton acting towards the left. Now, listen, we are asked to find the location and magnitude of maximum bending moment. So, you see, you look into the diagram, there is a 40 kilonewton concentrated load and a 10 kilonewton per meter UDL. So, this UDL is totally, it is 10 into 20, we have 200 kilonewton, this is 40. So, normally the maximum bending moment will occur in the region CB, in the right half of the arch. So, in order to find the maximum bending moment, we will consider x from B. So, B is the origin now. So, we will take x from B. So, we know at x y is equal to 4hx by L square into L minus x, where x is taken from B. So, bending moment at any section x is equal to, so mx is equal to this VB into horizontal distance x. See, this is, so any section right anti-clockwise is positive. So, VB into x positive. And for any section, if it is right clockwise, it is negative. So, it is minus h into y. Right clockwise minus h into y is negative. Minus 10 into x by 2. So, we simplify it, we get 160x. See, we are substituting the value of y. We are substituting this y in the equation for bending moment. Finally, we get 160x minus 150 into 4 into 10 into x by 40 square into 40 minus x minus 10 x square by 2. We can further simplify it. So, after simplification, we get up to this. So you can simplify this further. So we have to find the maximum bending moment. So from the calculus we know the maximum bending moment. For finding the maximum or minimum bending moment, you differentiate it with respect to x, that will be equal to 0. That is dou mx by dou x is equal to 0. So differentiate this equation, we get x is equal to 10 meter. Now substitute x is equal to 10 meter, we get the maximum bending moment mx is equal to 200 Newton meter. That is, the maximum bending moment will occur at a distance of 10 meter from B, and the maximum bending moment is equal to 200 Newton meter. So that's all for today. We will continue in the remaining portion in the next class. Thank you. Thank you. Thank you for listening.